This video is about testing equivalence. Testing equivalence. And the problem we are considering here is whether two different Turing machines hold on the same input or not. And if they do, they will be called equivalent. That's actually a very practical problem. You have two programs from different sources maybe. You would like to know whether they have the same behavior or not. That's a more general case of this equivalence problem. And we'll show that the equivalence problem is undecidable. First, I will give a formal definition of the equivalence problem. For the equivalence problem, we have to have two Turing machines, so we need two codes of Turing machines. I will call them W1 and W2, and I will use a hashtag as a separator to separate the two codes. W1 and W2 are binary encoded, and as a separator we'll have this hashtag. Could be any symbol, in fact. And in this set we have all the Turing machines such that W1 and W2 are some binary codes, and the corresponding Turing machines MW1 and MW2 hold on same inputs. Okay, that's the equivalence problem we're looking at, and the other problem for the reduction that we'll use is the emptiness problem. We'll show that EQ is undecidable by doing a reduction, and for the reduction we use the emptiness problem. The emptiness problem was simply the set of all Turing machines such that the Turing machine does not hold on any input. This is the one we know to be undecidable already. Okay, so for the reduction, again we assume there's a Turing machine deciding EQ. So we assume it would be possible to decide EQ. And EQ gets two Turing machines, W1 and W2. And it can decide whether it's EQ. They are equivalent, whether they hold on the same input. And this is the algorithm we'd like to use. And we would like to use it to decide E, the problem we know to be undecidable. So we would like to know whether the Turing machine holds on any input. So here there's only one parameter, and the question is, does the Turing machine hold on any input? Now, what we have to do is we have to come up with an idea what to give this decider here as an input that we can actually use. We would like to know if a Turing machine does not hold on any input. And we assume we already had an algorithm that could decide whether two Turing machines hold on the same inputs. So we might have the idea, okay, if we can decide whether two Turing machines hold on the same input, and we just want to know whether a Turing machine holds on any input, we'll just compare it with the Turing machine, this Turing machine that we get as an input here, with another Turing machine from which we already know that it does not hold on any input. Because it's actually quite easy to construct a Turing machine that does not hold on any input. We just put an infinite loop and that's it. So that's actually what the reduction does. We construct a Turing machine. I'll call it, let's say, MW prime, that only contains an infinite loop and does not hold, and therefore does not hold on any input. So we take one explicit instance of E, so one explicit problem we know to be in E, and we simply compare it then with this algorithm to our input W, for which we would like to know whether it holds on any input or not. And then construct pair W hashtag W prime. And this is actually the input here. We just input here W separated by W prime, where W prime is the Turing machine that does never hold. It's the simple one with the infinite loop. Okay, let's consider again both cases. First case is what happens if W is in E. W is in E, that means that MW does not hold on any input. Okay, if MW does not hold on any input, we compare it with MW prime. MW prime does not hold on any input. So MW and MW prime hold on the same inputs. Then MW and MW prime hold on the same inputs. And that is there in E. Consider the second one. What happens if W is not in E? We know that MW does hold, at least on some input. But if MW does hold on some input, it does not hold on the same inputs as MW prime. So then MW and MW prime do not hold on the same inputs. And that is that they are not in E. W prime, W hashtag, W prime is not in E. So in this case, we can simply use the same outputs that we get from EQ, from the EQ algorithm, for our new algorithm. And as we already know that E is undecidable, we can conclude thus the equivalence, that the equivalence problem is undecidable. So as E is undecidable, the problem EQ, the equivalence problem, EQ is undecidable.